Thank you. I think we're on time. It's a very, for me, it's very rewarding that so many questions, thoughtful questions. In fact, that's where the academic intellectual exchange and promote the further thinking is about. And so I think that today's second section, I will basically talk about the hydrology or the data of hydrology. And in terms of this book, you can see that it's chapter 3 and 4. So first we will spend, we have 2 hours roughly, so we'll spend 1 hour on the state infiltration, and that provides some kind of basic concept about the hydrological process in Kel's law. And then we'll talk about transient, which is explicitly deal with the time effect. We know that in reality, we never reach a steady state. A steady state provides a good way for us to understand why the water specifically will move from one point to another point. And in the transient process, I will also talk about one of the study that we have done recently is to answer the question, let's say we have a precipitation that fell on the hill slope. And from that point that you are concerned, is the water going to infiltrate into the soil or is going to run off? Now the water go into the soil, are they going to go vertically, or are they going to perpendicular to the slope surface, or are they going to move parallel to the slope? So now the direction of water once they go into the soil. That question, of course, intellectually is very interesting. You know how water moves, but I think also as a consequence to how the landslide occurs. Why you observe some kind of parallel to the slope? Why sometimes you can see the deep landslide? I think that has an implication of methodology. So that's what we're going to talk about. By the way, if you have some kind of a question you think that you want to ask, just raise your hand or just start to talk. Because sometimes we wait until the end of my talk, and you may forget, or you may become. So you can ask any time. I think that's a very important. So for this first half of the second half, what I'm going to talk about a few things. One is why the water will move in the slope environment. And then we will basically talk about what is the Darcy's law. Of course, I taught the Darcy's law in the previous talk. And in fact, if you look at the book, this part is the hydrology part before the stress part. But I think that given the stress, which I think is also important because it's kind of an important thing that we feel that in the physical process. And then we'll talk about, as an example of Darcy's law, Camilab. In fact, the Calabria is a transient process. In other words, people know that if you have a water table, the water actually will move upward above water table all the time. Because at the land surface, if it's not very deep, the land surface is always subject to humidity change and climate change. And so therefore, you always, from thermodynamic energy point of view, you always create the deficit, or we call it gradient hydrologically. So that process, unless you have a ring infiltrate, in that case, you're going to have a downward movement. Otherwise, you'll have a Calabria. And then we talk about vapor flow. Vapor flow is also important in cross-feeding in some circumstances because, particularly under the clay or dry environment, a lot of water movement, in fact, is not in the liquid form, but rather than evaporation condensation process. So we quickly talk about vapor process. And we focus on the vertical flow to see how the water moves in the vertical direction. Although in the hill slope environment, vertical flow is only one possibility. There are many other scenarios. Vertical flow allows us to put it into the framework, into the analytical framework, which we can see what are the controlling parameters: infiltration, hydrological property, and so on and so forth. And we also talk about as an example of what we call the hydrological variance. So now when we deal with the material, hill slope material, very often they are not homogeneous. They are anisotropic, not homogeneous. So what is the consequence when you have a rainfall into the soil because of layering, because the isotropic, the anisotropic condition? So we talk about a simple example of the hydrological variance, and then we give a summary of what we can learn from this time. So you can again continue to look at that book, and where's the book, a copy of that one. I think some of them, you can continue to circulate around them to look at that. So let's look at the first question, why the water will move in a slow environment. I use this cartoon to illustrate a few things. The water will move, what specifically we'll ask ourselves, we will have 2 points. The water is going to adjacent 2 points. It's going to move from one to another point or vice versa. So to answer that question, you actually can look at different mechanisms. So if you look at the process here, this is of course is a kind of a typical hill slope, but of course every slope is different. And you can see that because there's a topographic difference, because the land surface above the land surface is atmospheric, which is subject to climate change due to the seasonal, due to the even weekly. It's different in terms of hydrologic condition. We talk about humidity, we talk about precipitation, we talk about temperature. Therefore, the consequent subsurface, how the water distributed, is quite complicated. But given for that, you actually can kind of look at the different regions. So here is in the typical, we call a steady state condition, you have a water table, which is divided saturated and unsaturated. And then away from the slope, you most likely you have a gravity. So gravity is one thing important because gravity always put toward the center of Earth, or we call vertical directions. And so away from the slope, away from the surface, then you will see vertical. But then the water is going to go to horizontally because of the discharge. Typically they have a spring. So then the topographic relief, water relief reduced hydrologically is the head differences. So the water typically will actually go. Of course, the some groundwater will recharge to water the deep groundwater. But we talk about shallow. And then around the water table, there are several processes. In some areas, you can have a table rise because of the potential differences. And then you can also have the humidity gradient between the atmospheric and subsurface. And of course, you can have the gravity and capillarity, which both acting to flow in the hill slope. So those are the basically the possibility. But if you look at the mechanism why the water will move, it's basically under gravity and under the humidity change. Now we talk about as I said, between the atmospheric and so gravity and the matrix suction. Sometimes we call it matrix suction also is because of the change in motion time. So if we want to unify that one, it is we can do that. We can do that by energy concept. So the energy concept is if I am interested in the hill slope, the 2 points adjacent to each other. If I want to answer the question whether there is a water move from one point to another point, is to look at the energy level. If I give a unit of volume of water, to see how much energy is stored. So energy could be stored in a different way. I will talk about the next one. It could be in the gravity, it could be in the pressure, it could be even in the salinity. Sometimes we call osmotic. And then to compare with the next point, the 3 components, and which components the summation is bigger and small. And the thermodynamic is second law, so that's a kind of fancy term, but in terms of generally, we know that it's a law, it's something we observe, we can never prove. This energy always, the flow goes from high energy to low energy. So that's the thermodynamic second law. And hill slope hydrology is basically it's a statement, the amplification of the natural phenomenon of thermodynamic second law. So let's first, very important I find that is a basic concept that we go to different disciplines. Very much so, people define differently. Some people call the head, some people call pressure, some people call chemical potential. So, to cross one concept to another concept, sometimes this is like a basic building block. And I find that a lot of people immediately get a block. Now will not be able to exchange the idea because of the basic concept. So, in fact, all these three, I put the head, pressure, and the chemical potential, they talk about the same thing. So, next couple slide, I want to explain that. So, this is basically assuming that people have a very little background about the concept, but I also think it's important. So, let's talk about what is the energy per unit of weight of water. So if you look at the unit weight, now we use a certain kind of mass. So energy per unit weight of water, if you look at the definition, it's actually exactly, people sometimes talk about head concept. When we talk about head concept, the total head of 1 point is 5 meter, 10 meter. We actually talk about the energy per unit of weight of the forward. So I can show you that because if you look at the total head, so energy is a force times distance. That's what we call energy, right? So the most easy way to call energy. And then the unit of weight, which is a force. So when we talk about weight, it's different than mass, right? Mass is how much matter it is. Weight is under the gravity, so it's a force. So if you do that, you will see that what is the unit? The unit is a meter. So that particular meter, in fact, when we say we have a head, total head of 1 meter, which will basically say how much energy that in the unit of weight. So that is the one concept. It also sometimes we say differently. Sometimes we can ask the question, what is the energy per unit of volume of volume? So now you see the differences. One is a unit of weight, one is a unit of volume. When we answer that question, that will automatically lead to very logically to the pressure concept. So if you look at when I define the energy, so again, energy is force times distance, and then divide by the volume. And if you do that, and you manipulate that, you will find that eventually it becomes newtons per meter, the unit area, which is exactly the pressure concept. So when we say the flow pressure is negative 1 kPa, it will basically say how much energy per unit of volume of water. So that is the concept. Then you ask me, well, how can I convert this to head concept? I will talk about later. Now the third one also popular is people will ask how much energy per unit of mass of the flow. So these three differences looks like very trivial. In fact, it actually make it very different. You see the first statement and the third statement, what's the difference? One is about the unit of weight, one is about the unit of mass. So when you try to do that, you actually come up with another way to describe how much energy in water. So basically, if you follow the definition, the energy divided by mass, you use a mole, and then eventually become how much joule per each mole, per mole of water. So these three things, it's all when people come together. Sometimes I go to AGU, I go to. So if you look at what are the relation among them. So in the book I published that. You actually can convert these three. So for example, if you want to know, so the vertical is a chemical potential, how much per mole, how much joule per mole, head, meter, pressure, and then you put horizontally, and you can do a conversion among three of them by some common values. So when you see the different disciplines, they talk about the textbook, the journal paper, talk about meters, pressures, kPas, as well as joules per mole. And in fact, we all talk about the same thing. The bottom line is to describe energy per unit something, per unit volume, per unit mole, and different kind of describe about energy level. So that's a conversion, and you can spend a little bit of time if you want to do some exercise. Where I say, okay, the pressure is 10 meter. That's equivalent to how much the kPa or how much joule more. You can do this exercise and convert. So the other question we want to say, how is the energy stored in cold water? In other words, in what kind of form can they store? When we talk about the static, which means we don't talk about weight propagation, we just talk about under the static condition. It could be an energy if we take a unit of cold water. It could be stored in three forms. So it could be in the gravity, it could be in the pressure, and it could be in the osmosis. Very specifically for these three forms, you can use what we call superposition to define total head. In other words, if you think about total head, if I give a unit of volume a unit of weight of cold water, the total head will be under gravity, under the matrix suction, which is the pressure, negative pressure, and under osmosis. Now, I do so actually use a very big assumption, and that assumption actually is questionable. In other words, you see that I add all these three components together. This is something that has been still under intensive research, some people think it's not a single position. For example, the osmotic pressure, if you think about pore water, this is defined at the unit of pore water, but it can be defined at the unit of soil. And because there is an interaction between the clay mineral surface and the chemical solution, so that the concept of these two could be a couple effect. In other words, we do right now we make assumptions, so each of them could be applicable. So that's kind of assumption which has been proven, generally speaking, quite well, but under certain scenarios it may not be known. So that is mathematically too. If you do mathematical Taylor's expansion, you can always get a zero term and then get a high order, which is a couple term. This is the first assumption. And each of them actually you can quantify. In other words, you can precisely define it. For example, the gravity, the head in terms of gravity, it's basically the vertical distance above whatever the point that you want as a reference. Could be in the sea level, could be in some other any part of the point that you want to reference. Above that, at that point it is zero. Above that, it will be defined as a value based on the distance measured directly in terms of length. And then the matrix suction, which is actually in this case how they depend. So here is a very important concept. This is actually the concept where the soil characteristic comes from. Is for a given soil, that part, now the water pressure is actually a function of the moisture content. And specifically, they are negative value. Negative accounts for they are lower than atmospheric condition of pressure because it's the nature of the insaturated condition or above water table. And the third one is also related to the concentration of the material. The concentration of material, in fact, it could not be in this way. It's a Van equation, which is linear, and now the concentration directly related to the osmotic head. But some material, when you have a high concentration, it may not follow linear equation. But generally speaking, you can directly correlate. So three of them actually depend differently. One depends on the vertical distance, which is gravity, and the other one depends on the moisture content, and the third one depends on how much it dissolves the material in the solutions. Let's look at each of them, gravity, how it works. So gravity, for example, if I draw this hill slope, we have the water table at the toe of the slope, and inside the hill slope, and you can, if it's under the very simple case under the condition, you can think about define the linear above the sea level, and that is the pressure head for the. The second one is, as I said, it depends on moisture content. So if you want to be a little more precise, that's where we start to draw this what we call soil characteristic curve. You draw the horizontal as a water content, vertical as a head potential in meter, and the up direction, which is a positive, but mostly because we are negative, so it's on the negative side. And for each of this different state, I use three different states to represent. It could be the so-called pendulum state, it could be the called funicular state, which is you have continuous water. Pendulum means each of the water body are kind of somewhat isolated. And then you have a continuous, which is overlapping. And then you have this Camilab state where actually the ancestral air, the air portion become isolated. But between that is a kind of transition process. That transition may be smoother for one soil than the other soil. But if you do that for a given soil, they will have some what we call characteristic function. Now they always follow for one vertical state, always follow one line between the head and the potential. What that says is if I want to know my soils under unsaturated condition, how much head or how much energy, I need to measure water content. Because if I determine the water content, I can come back to this curve for that particular soil, then I can pinpoint to how much energy for that state. Of course, the computation will know that for given soil, depending on the state, that curve could change. Wetting and drying will be different. But generally speaking, we have this concept of a soil water retention curve. As I started to use two concepts, we already talked about this equipment. One is the so-called matrix suction head, which is a positive value. You see that because we subtracted the matrix suction, which is originally a negative value, from the air pressure, so they become positive. Sometimes it's generally called matrix suction. And we do so basically is to refer to ambient atmospheric pressure. So the ambient atmospheric pressure. But one thing when you study landslide, what we find that in recent years, you have to be very careful when you use a matrix suction, because the matrix suction change, the atmospheric pressure change actually has an impact to the landslide. For example, just to talk to some of you, in Colorado, in the US, where the state I am, we have this called Slangolian landslide, which is about 5 kilometers wide, 10 kilometers long, in the big valley, and that movement has been in the last 100 years, every year is about 10 meters. And recent studies show indicating that, in fact, that movement has a lot to do with the atmospheric pressure. Because if you measure the atmospheric pressure every day, day and night, it's going to easily change 10 kPa, 50 kPa. But if you change it on the surface of the atmospheric pressure, it does not necessarily say that the pore pressure is going to immediately change it to 10 kPa. So what that means is that you're going to create a deficit of this matrix suction. And that itself could be sufficient to, in this case, trigger some landslide, Ning Lu. So we have to be careful about that. But for now, we basically define that as a matrix suction. The also example of matrix suction, what you would expect if you look at the Helms law, say, is it where the matrix suction is bigger, small, and how it varies. And that depends on whether it's drying or wetting condition. So I'm kind of just give throw the number there. If you have a drying state like today, or after rainfall, then the surface start to have a humidity, generally speaking, much lower than the subsurface. You can have evaporation. Near the surface, it could be in the 10 minus 100 to 1,000 or even higher kPa, right at the land surface. And in fact, in the atmospheric, it's almost a shield. It's like a minus 300, 100,000, 300,000 kPa. Because why, for example, like in today's humidity, if you look at the humidity and matrix suction, they are related. And they're related by what we call Kelvin's equation. So today's humidity, for example, I will guess 40%, 50% humidity. And if you convert the 40, 50% relative humidity to matrix suction, it can easily convert you to 100,000 or even higher kPa of suction. And that is another reason why you have when you don't have a rain, you have a general evaporation, because the energy in the air is much lower. Remember that minus sign, right? And then the subsurface, and that is promoting based on the thermodynamic second law that energy, the water flow from high to lower. So high is in the ground, lower is in the atmosphere. In fact, all the plant, we see the other vegetations, plant trees. The reason they can survive is Mother Nature creates a perpetual environment for them. And so therefore, the tree can not pump the water, but automatically, because subsurface you have a high moisture, so the potential is higher than the atmosphere. And then you have this promoting this capillary in the plant tissues, and they go up in one direction most of the time. So that is the condition. Now, under the wetting, let's say you have a heavy rain. So what happens when you have heavy rain? In the wetting condition, then you can have a land surface. If you almost pump in the water, that means it's about zero matrix suction. It's almost like a pore pressure to zero. And that's kind of a trivial condition. But then inside the slope, then you can still, because there's a time delay, you can still have a negative matrix suction there. And that actually promotes the water to flow into the slope. So the reason, as I will talk about later today, is the second part for the end of this morning, is the driving force for water in the hill slope is gravity and the matrix suction. And matrix sometimes can operate in a favorable way downslope. But sometimes it can also in a favorable way move to downslope instead of vertical. So the combination of that, it could be a quite complex. So that's a kind of just draw idea about the value. And this value is given that you actually very often people ask and say, I'm going to measure the pore pressure or suction in hill slope. What kind of sensor I'm going to buy and what kind of range? Because each sensor has a different range. And then you have to have a good idea about what kind of soil you have, what kind of climate condition you have, and the result in the hill slope, the likely range of your suction, and then you can get a proper instrumentation to measure the suction. The osmotic, the flow about the osmotic suction, it only depends on purely depend on the concentration. So here is the drawing of osmotic suction, the dependency of osmotic suction on the concentration. Typically, if you have the line between that is the temperature, because you see the equation, it actually depends on temperature. So the osmotic potential depends on temperature, so that's the dependency. But generally, if you have a higher the concentration is, the higher osmotic suction is. So it's suction is not pressure, which means that they are generally indicated negative. So in other words, if you have a water, pure water, we define the water potential as a 0, osmotic potential as a 0. But as the salt dissolving to water, they become less than that, more and more negative. Now lower and lower. And that is the reason if you do this simple experiment, what we call the semi-membrane there, and if you put a fuel on one side with the fresh water, the other with the salty water, you're going to see this kind of osmotic movement. You're going to see some kind of what we call osmotic pressure. It's because by dissolution of mineral in water, the water potential becomes lower. So if you have two sides, one side has a dissolution of a salt, the other one does not have it. So this side has a higher potential because of the 0 salt, and the other side has a low potential. So based on thermodynamics, second law, this is going to flow in that direction. And if you put this semi-membrane, which means you allow water molecule, it's just the perfect size, allow water molecule to move. But the salt, like sodium chloride, usually are much bigger than the water molecule. If you put the seed here, then you're going to create this kind of hydrostatic pressure, which is what we call osmotic pressure. So osmotic pressure actually is a way to lower the potential of water. In fact, it has a biological effect. For example, if you eat a lot of salty food, what are you going to feel? You want to drink water. So that's osmotic suction, right? And because your salty body has low potential, you want to have a pressure. So you can affect your sense of human sense. So that's the osmotic pressure. Although it's not directly related to landslide, but I think that they are in the area of the coast area because in the groundwater, the fresh water and the salty water never become, it's a dynamic process because the tidal movement and the groundwater movement are seasonal. So it may have some impact in some of the coast areas of the ocean process, but it's still under the study. But generally speaking, we put it there because we want to be a little bit more rigorous friend. So the other thing is I want to mention about this local thermodynamic equilibrium concept. So this concept, because the reason I want to mention that, I want to talk about that is because when we deal with the hill slope, we deal with water, solid, and then air. Very often we ignore about air. Air is so important, the poor air I'm talking about, because it has a huge effect near the surface, whether it will evaporate or whether it will condensate. In fact, it is the one I mentioned that it's going to drive the exchange of the molecule. So the local thermodynamic concept also has an impact to how we're going to measure pore water. For example, most of the measurement technique summarize each of them in my book of one chapter, but I will mention quickly tomorrow, not extensively. Is in many cases we cannot directly measure pore pressure under negative condition. Most direct way that you can measure negative pore pressure is up to maybe 100 kPa minus. Very often we know that the soil pore pressure could be a minus easily, way below minus 100 kPa. How we measure that one? We have to measure, so the current technology is we measure the humidity in the pore air, because you can use a humidity probe to accurately sense how much humidity in your soil or in your field system. And that humidity actually you can convert to pore pressure. How they convert that one is thermodynamic local equilibrium. So if you look at this cross median, if I put a box there and indicated that there's a liquid there, there's a solid, there's air, and there's an interface. The interface curvature is the one that determines the equilibrium condition. Then with the air, so I put in the air, I said the air is constant certain kind of humidity. Even initially you put certain kind of humidity, they may not consistent with the energy level in the little menisci. If that's the case, then it's going to have exchange, depending on which side the energy level is high. And so I can put it into the total head concept, because we just talked about total head concept. The total head concept, all the energy stored in the water has a metric pressure form, gravity form, and osmotic form. It has to be equilibrium with the total head in the air or in the core air. Because we make assumption that the air in the in telescope is connected to the atmospheric or the environment ending. So if we do that, we can put an equivalent of the total head to relative humidity. By doing that, in fact, you can measure the total potential of water by measuring the relative humidity. The specific technique, for example, is called psychrometer. The psychrometer is one to measure the relative humidity that it can be used to in soil to monitor the cycles. So that is the concept of the equilibrium. And we also want to talk about relative humidity. When we talk about relative humidity, what we talk about? We talk about actually relative to what? We talk about vapor pressure concept. So what is the vapor pressure concept? The vapor pressure, if I have a cup of water, let's say I have a cup of fresh water, and half of that, if I close the chair, initially, of course, the air will equal to today's humidity, say 50%. But if I cover by the top, and then wait for a little bit of time, when they reach equilibrium, the liquid phase and the vapor phase reach equilibrium, the humidity will be how much? It will be 100% humidity. Because the process is when I close, the moment I close the lid, even though the air is 30% and the water is 100% humidity because it's zero energy. So it will promote the evaporation. And because I close the lid, so the humidity will increase as the evaporation process continues. Now you ask the question, when the process is going to stop? It's going to stop at what we call 100% humidity. So sometimes we call saturated vapor pressure. Because for a composition of air like nitrogen, oxygen, certain amount, they can only allow that much of water vapor into the air phase. But then it's highly dependent on the temperature too. Because as we know that's why we have a shower, we have rain. It's whenever the humidity reaches 100%, what's going to happen? It's going to have condensation. It's going to have rain. And that's the nice thing about climatology, is about this relative humidity. So the humidity, we call it saturated humidity. You can actually draw a constitutive relation between the saturated vapor pressure and the temperature. Or you can draw a saturated vapor density, because vapor is considered as an ideal gas, so you can calculate that by vapor pressure, you can calculate the vapor density directly by using thermodynamic constants. So that relation typically, although it has never been rigorously derived, that can only be possible depending on your assumptions. But most people you can check with the steam table. You can find a relation between the temperature and the saturated vapor pressure, and also the corresponding the vapor density. From there, you will define today's relative humidity, because most likely it's lower than that. Very, very real in the case you measure the air humidity equal to 100%. It's almost you have to be in the middle of the storm for a sustainable time, and then you measure the humidity is 100%. Other than that, it's always less than 100% because the environment at a much larger scale, it's always lower than 100% humidity. But you can characterize the saturated vapor pressure, and you can also measure the prevailing, the current vapor pressure, and the ratio of that will give you so-called relative humidity. So from that line, I can draw, depending on what kind of relative humidity you have, you can actually see what is the vapor pressure. This diagram, for example, if you look at if I say, okay, today's 60% humidity, today's temperature is 25 degrees. So what is the vapor pressure here? So 25 degrees Celsius, and then you go to 60 degrees of humidity, and you can see the vapor pressure. And you can also see the corresponding saturated vapor density. In other words, if you read these numbers, they give you 25 here, roughly about 15 grams per cubic meter. So if today's humidity is 60%, I can say that each cubic meter you're going to have about 15, 25 here, about 15 grams of water vapor. What that says is that even today's temperature suddenly drop, let's say temperature drop incredibly lower, then let's say the temperature suddenly drop from 25 degrees, of course it will happen today, but if it drops from 25 degrees to about 15 degrees, it's going to be 100% humidity, right? So it will be 100% humidity if you drop that one, and which means if the temperature suddenly at the high atmospheric, it's dropped to 15 degrees, and then you have a rain because it reaches 100%. So this basically is a cycle the kind of topology. It's basically this kind of thing. But this provides a background, some background for later zone. Let's look at now let's turn to our objectives. We concern about Hill's slope hydrology. It actually has two parts. One is a below water table, which is in the vein of a traditional hydrogeographical problem, deal with the larger scale, how water recharge and aquifer. And the other part is what we call data zone, which is above water table. Above water table, in fact, it's below water table. We know that if we plot the saturation, it is 100% saturation. So saturation is constant. Above water table, it also actually has an area where the water still keeps saturated and then start to desaturate. And at some point, it will reach some what we call residual state water content. But if you look at the head, if you do not have any water movement, your total head has to be the same. Right? So that's the thermodynamic statement. If you don't have the water movement, we call it hydrostatic case. Your total head has to be the same. But does not mean that if you measure the pressure concept, the total head has an elevation and pressure. And you see that you are concerned about the elevation head. Elevation, if I draw from here, it's 0, and elevation actually is going to increase the head. So elevation head is going to increase. Because the total head of the elevation head past the pressure head, in fact, under hydrostatic condition, you measure the pore pressure. Below water table, it's a linear increase. Sometimes we call it hydrostatic, like a swimming pool or reservoir. You use a hydrostatic to estimate how much pressure below the water surface, right? So that's the linear now. In fact, it's also linear above water table. It just go negatively by distance. So that is the under hydrostatic condition. Why it's linear is exactly this equation, because this one is linear. So if you flip this one to the other side, you can see the pressure. It has to be an opposite side of the linear. So that's the negative pressure on the hydrostatic condition. This one, it explains under the case, ideal case we call hydrostatic, which means total potential is the same everywhere. There's no flow in the Hill's slope above, below water table. What you're going to expect to see the moisture content distribution, what you're going to see the total head, the elevation, and most of the concern is what is the pore pressure. So it varies under hydrostatic condition. It varies, but there is no flow here up and down, saturated section. That's not the real case. Real case is always some disturbance under different kind of condition. But this gives you some idea about what we can measure that, what's the happening etc. Now I'd like to again when I prepare this book, particularly also this part, I assume that the audience has a very little background about too. So we all go back to some of the earliest book we call the Darcy's experiment. What I'm drawing here is Darcy's apparatus, original apparatus, and then original experiment data. And this slide somewhere is not going to see the double shape, which should not be there. So I just can't appear there. But anyway, Darcy conducted this experiment in the sandy soil. What he has done, as you see, that he manipulated, it's all undersaturated condition. So he manipulated the top flow in and flow out, reaching steady state, which means when he opened the valve at the top, he will allow the observation until the bottom flow out is the same with the flow, and then start to collect the water. When you collect the water, and then you will plot the discharge velocity, where the hydraulic gradient that you will apply, or you can measure from the piezometer, as you measure from the piezometer, which is the top and the bottom. Each of them has this simple distributive arrangement. And you find this data, and that data, from that data, it shows that very interesting behavior. The proximity is a linear number one, so in other words, proportional to your gradient. And the second one is, you go back to zero. What that says is you can use this type of linear equation instead of classifying the constant. So That is no intersection. Zero gradient without zero flow. So that is a simple we call Darcy's law. It's a law that observed by Darcy. And of course, that law that we laid out, we can calculate that it follows the thermodynamic second law. Because here you said the total head, even there is differences of the total head, you will have flow. If there is no difference in the total head, you're not going to have flow. Of course, the total head will be in the free form, as we mentioned. Elevation, which is gravity, pressure, as well as the osmosis. But in the case of this is saturated, it's also valid for unsaturated case too. So for the transient solution, another case which is non-steady state, the Darcy's law is talking about a point which is in the steady state. Because in reality, we concern about two aspects. One is the flow will never reach the same point at each point because it takes time to reach equilibrium. So how long it will take? What is the spatial distribution of the head or specific flow is our concern. And that belongs to one of the application, as you see that even from Darcy's law, you apply that to steady state unsaturated condition. You're going to introduce two characteristic curves I talk about. One is the relation between hydraulic conductivity, another become function of constant, become a function of modular content or matrix sucking. The other one is the head itself, the particular matrix sucking head. You notice that I spread the total head into three components. Assuming the osmotic component is zero, in other words, there's no salt effect. Then you have the gravity and the matrix, which is the pressure. And then the gravity one, which is equal to z. And then you simply become one, take derivative. And you can have a second head. So this is the reason I put it out is an equation, Darcy's law under such a condition is, even for a very simple problem, like to answer the question, what is the flux at a specific point, by Darcy's law, you have to use a two characteristic function, which is sort of the potential, as well as the hydraulic conductivity functions. So that is so how the soil water retention hydraulic conductivity looks like. Here is the soil water retention could look like represented. Vertical is a matrix suction, horizontal is a water content. And I use this as a KPA instead of the head values because of the conversion as a showed here. This for convenience. So depending on the same will be actually like this. They remain saturated, but at several kPa it's going to be desaturated. And once they start to desaturate, they drain pretty quick. And at some point they're going to reach a steady state. So there's a similar but much higher in terms of when they're going to be desaturated. And the clay is high. So that is the general pattern of soil water characteristic of the retention curve. And because finally hydraulic conductivity, the soil water characteristic curve also show the hysteresis. Now we talk about. Sorry, somehow they have the shape. The historical effect is specifically talk about when you have a saturated drying, so this is called drying process. It will be different than the wetting process. And that difference is to be quite huge. What that says is even though, as I say, moisture content, it can have a two equilibrium matrix action. It depends on the wet and dry state. And the two equilibrium point will be very different. If I give a point 3 as an example, you know, the horizontal is the section of the pressure difference is very different. So that created a lot of challenges. And the current challenge, I will talk a little bit more, but basically, virtually most of the method to measure soil water retention is drying method. But how can we do that for landslide? Because the landslide are mostly in the wet condition. It's after rain, and wet stuff infiltrating the soil. And so that becomes very challenging. I will talk about the methodology that we developed in the last decade to be able to measure both curves, drying and wet conditions. So that's one of the challenges of soil water characteristic curve. We can also look at the hydraulic conductivity function. Hydraulic conductivity function in this case is the dependency on matrix suction. Yeah, I don't know. The hydraulic conductivity function also depends on matrix suction. See, in this case, it depends in a very, very interesting way. I give two soil. One is sand, the other one is silty soil. which is good for agriculture. The same one, if you look at the saturated hydraulic conductivity, they are higher than the silt, which is very intuitive with saturated condition, right? Sand has a larger pore size. But as they desaturate, you will see that at some point they're going to cross over, which means the sand hydraulic conductivity function is going to reduce much faster than the silty soil's hydraulic conductivity. So you cannot, in such a soil, you cannot say like permeability of sand is always bigger than permeability of silt. It really depends on their relation. And that function is what we call hydraulic conductivity function. And also, you will see that this is real soil. They can change a carrier fluid 6 order magnitude. For example, like sand, from 10 to the -3 centimeter per second at the saturated condition to about 70% moisture content saturation to 10 to the -9, 10 to the -8. So 6 order magnitude. So it changes a lot, but the basis of water flow speed can be changed 6 order magnitude if you use the same hydraulic gradient. So that changes the dynamics of entire water movement in the very slow environment. Now, so let's come back to the uncertainty zone, right? And the hydrostatic combat. If you look at the hydrostatic condition, which is a special case where the gradient is 0, what you expect from water table, above water table, is that you're going to see the below water table we'll talk about is all saturated. Above water table, the moisture content will remain constant or saturated, and at some point it's going to be desaturated. And this is very characteristic for all soil. But the height of this one depends on the soil. And sometimes we'll give a term called capillary fringe. In fact, if you go to the beach, you can actually literally measure how much the capillary fringe is by digging a little hole in the sand, and you can see what the sea level, what is the saturated the sand above that sea level, and then above that, beyond that point, actually it starts to desaturate. And you know that if you have a saturated soil, you cannot do a sand castle because the conversion to suction stress is almost 0. Same thing for the dry soil. But come back to this is what you expect under the hydrostatic, which means there is no flow, or total potential is constant. Well, the reason I want to draw this curve, this is the curve. What is this curve? We have another name, we already use it. This is exactly what we call small water characteristic curve. In fact, go back to the early of the last century by a guy called Buckingham. I showed you the first 2 slides. When he first measured this saltwater characteristic curve, he just used a column, put a sand column. Initially, you can have an all saturated, let it drain, and wait for a few weeks when nothing happened, no flow, and then you measure each of the segments, look at the water content, use an oven dry, that gives you this curve. That gives you the measurement of saltwater characteristic curve. So that's what happened. But if you do the experiment the other way, let's say you will have a column of sand, which is dry initially, and then you introduce water from the bottom, and then what happens? What happens is the water is going to seepage upward, called capillary rise, and in a saturated way, and then start to desaturate, and it will go up until certain points. So how high the capillary can go up, it also depends on what kind of soil you have. Because eventually it's complicated, it's hard to predict. There's no theoretical, it only have empirical, because it requires water to kind of seepage up. But the water movement up is also complicated. There's a water movement in the continuous pores. There's also water movement we call the film water, which has a lot to do with hydration, in other words, the surface and grab the water. So, for example, like clay actually water can seep very high. The reason is beyond certain point, even if you don't have a capillary water, you can have a surface hydration water. And hydration water can move upward, just like a tree. Most of the tree tissues, the reason you go to 20-30 meters on top of the tree, you still have a moisture in the tissue is not because the capillary water, it is most of the tissue's ability for hydrate, and the hydrate will do. So that's a capillary rise movement. Just like in soil, in some ways, very similar to the plants. Just plant is much more easy because stand out of the ground, but underground, in fact, this happens. So what happens is, if you have a capillary rise, basically, at the surface, if you continue to provide a very dry environment, if your carbon rise can reach the surface, which is not always true. Some soil, they cannot reach the surface. So they can only creep up to certain and start entering within. Some soil, you can have a reach between the water table and the ground surface. Now, if you have the condition, if you promote an evaporative condition, what happens is your soil is going to have a lot of salt after a while. So that's why a lot of agricultural soil, after a while, they cannot do anymore because the water is going to go up and then it's going to evaporate, but the mineral is going to deposit. If you go to the United States, southeast part like Texas, you have a lot of the soil which has a very thick, white calcium carbonate material. It is under the long time of the pumping of this carbon movement. And this problem also occurred in Australia. When British people they put a bunch of fishermen to Australia, and they start to treat Australia as England. So they plant wheat, right? They have a land, they have wheat. And Australia is a desert. We know that the distance between water table and the coast area is very high. But when they do this agricultural irrigation, the water actually percolates goes downward, and then they connect it with the Calabria finger. So when they connect it, what happens is it goes all the way to up. So to promote the evaporation, and then Australia, because it's a desert, most of the water quality are not good enough. It's very high salt content. So after they do this wheat farming for a while, it's going to useless. The land becomes very so salty, you cannot do farming anymore. So the Calabria rice is a phenomenon actually pretty widely spread, very interesting natural phenomenon. So the question about the Calabria rice, there are two interesting practical questions. One is how fast it's going to move from water table to land surface, the number of weight of Calabria rice. And the second one is how high we talk about this critical height where they can go. So these two questions actually has been one of the interesting topic in data zone hydrology. People try to study, try to understand, and try to build a theory. And the answer to how high the Calabria rise is, somewhat we know much better. And how high it is actually still quite unknown. A lot of empirical formula, but none of them are quite general. How fast it will be, nowadays you can do a numerical modeling, but you can also present it in a empirical way. What I show you here is a very early work by Pazaki. Pazaki basically established this relation between the wet farm and the coordinate z, which is the time. And the z is the wet farm, and the time is the runoff time above water table of the z distance. And that relation between these two. And as you see that the number of partial parameter, n is the velocity of the cross median, k such is the saturated hydraulic conductivity, because it directly solves the Darcy's saturated equation, and hc is the height of the Calabria rise. So with that parameter, you can actually find a relation between the wetting farm and the Calabria rise. And if you plot Pazaki's equation, which I show the Calabria rise versus time, the transient process will follow that line, follow this first line, and different soils. And sometimes in the early last decade, we developed a theory which consider about unsaturated soils hydraulic conductivity. Okay, we talk about it. And we do that, we develop an analytical solution, much more generalized than Pazaki. You can reduce to Pazaki, we consider about saturated hydraulic conductivity. But under unsaturated condition, we introduce air entry value. If we do that, we can develop another equation, and that equation actually predicted compared to the experiment data, which shows the second proof with the experiment data much better than the previous one for Calabria rise. But generally, when you feel that the Calabria rise is a phenomenon, it's a transient phenomenon, it's there in nature in many cases. Because most of the time we don't have a rain. When we don't have a rain, when infiltration is not downward, generally speaking, the water table is not too far away from the land surface, you will have a Calabria rise evaporation process. People study soil science, you know that if you have a downward movement, you can also bring a mineral down to a certain layer and form some kind of rich mineral deposit. But vice versa, you also can form a near the surface. And that's the result of the Calabria rise. Now we can move to talk about another case which we call vertical flow. So vertical is assuming only go vertically. Of course, strictly speaking, it is not necessarily valid, as we will show you later. But it's a good assumption when you have a gravity dominated, because gravity is always go down. But the second factor, as I said, due to the matrix suction gradient, it can go any direction. You can go up, you can go horizontal, you can go inward. Well, under the vertical condition, again, then you talk about the mechanism of gravity as well as the matrix suction, because initially soil is dry, you have a rain, and then both directions are in the vertical direction. So you're operating under both directions. So we can talk about the vertical flow system. What I show you here is basically start with Darcy's law, and then make assumption of the permeability, because of two characteristic functions. Permeability function and the soil water retention. You will make an assumption of certain model, and you can find it analytically. So what we show here is you can solve the matrix suction vertically profile, and that question actually looks complicated. It's not complicated at all. It's basically saying how the matrix suction depends on the vertical distance z, which is above water table, and that depends on the parameter, the air entry value. What is the horizontal, what is the vertical flux on the land surface? Of course, we are assuming steady state. It could be evaporate, it could be infiltration, saturated hydraulic conductivity, and this is about Z2. This is air entry value, nothing else more. So basically, you can use this one to get a first estimate about the moisture profile and suction profile. This is moisture profile, this is suction profile. So if you do that, then you can plug the parameters using a different soil. In this case, the first case shows the sandy soil. This is problematic for the presentation of the double. The sandy soil and the sandy soil and the clay soil and the hydrostatic condition. This is the first hydraulic conductivity function. And then you can look at the different scenario of different soil. I won't go into the detail, but I'll just show you. You can actually play the parameters. If you characterize the material property and setting property, like air entry value, quasi distribution. Yeah, if you know your area's average infiltration, you get a rough idea about how your moisture suction distributed in your soil. And this is the case for the single layer. And then we can move to the different layer to different parameters. And in fact, this morning I used this as a basis to look at what's the suction stress. But essentially, you can use this simple analytical equations to estimate what is your saturation water content, what is your matrix suction, and the different infiltration and evaporation. So I guess with that, I think we basically are going to finish the layer part. And the second part we want to do is under some heterogeneous, which is due to the barrier. So what I'm talking about here is the Calabria barrier. The Calabria barrier is due to because the material are different. In the case, basically you have a fine material on top, and then you encounter the bottom and the coarse material. Because under that circumstance, you actually can have a water basically resized on the interface. In other words, they can accumulate there, even saturate for a certain distance, and then you can break through. But of course, it depends on whether you have a flat interface, which is on that area, or you have an inclined interface. And that condition will make it equilibrium different. So we can actually estimate that using this simple concept. So what I explain here is why you have when you have an interface. In this case, the interface is not put in the vertical, horizontal way; it's put in the vertical way. So in that case, if you look at the thermodynamic equilibrium, which means the matrix suction equals the same as the interface, it will lead for a different water content. Now, if you have a fine material, I use a little tube compared to the larger tube of coarse material. When you reach, let's say, initial conditions, it's like that, and both sides has the same water content. But that results in different matrix suction, as we know that each soil has to follow that different characteristic. The result is such that actually fine material will have more negative, so the suction will go into one direction, and then will reach equilibrium. So in this illustration, all the water will retain in the fine soil. And that is the Calabria barrier. Basically, this is horizontal way. if you put a vertically, and those ability of fine soil, of course, will make a retention of the water. So if you just put vertically, the difference between what I call horizontal and vertical is in the vertical direction, you have to use gravity. They have to overcome gravity. So you can only, in the horizontal case, it's the equilibrium. The equilibrium condition is finally all the water will go there, and then this interface will have the same with that interface. So they reach the same kind of equilibrium. But in the vertical case, it has an additional driving mechanism, which is gravity. So that the mechanism will still will accumulate. But at some point, when the gravity is sufficient to overcome that, and the water is going to move farther. And that point of what we call a critical is the Calabria barrier capacity. So if you do experiment, you're going to see the fine soil, and of course, you see the water infiltrate and then accumulate. At some point, it's going to break through. And what we usually can actually find is breakthrough, which has to do with the breakthrough height, which has the accumulation height actually has a lot to do with your air entry value of each of the material. What is the air entry value for the coarse material? What is the air entry value for the fine material? So this is the barrier for the typical horizontal. Now, if you have an inclined condition, which is in terms of environment very often, you're going to have a slight modification. It's the same principle. And I show you here, people can develop analytical as you see the air entry value difference between the fine and coarse. But of course, you have what is inclined angle. It has a lot to do with the inclined angle of the interface too. But you can also still use that to estimate the ability of the Calabria barrier. Finally, before the break, I want to talk about the saturated condition. When you have a material which has different hydraulic conductivity under saturated condition, it will promote a different flow field. For example, if you have homogeneous material under the Hell slope, most likely the arrow showing the flow direction, you're going to go flow in and will come out. This is assuming all saturated condition. But if you have a layering, then you will have the head distribution is going to be different. They're going to promote a different pattern, more horizontal on this layer. But if you have a horizontal instead of an inclined layering, then they're going to have also different pattern. And if you have a vertical, low fluidity, high fluidity, they will have quite different than others. So those are the hydrological impact. If you're interested, you can look at my book. I'm more careful, and actually this is work by one of my colleagues, Mark Green, U.S. Geological Survey, wrote a JGR paper that specifically studied about the groundwater effect for saturated condition. So I think with that, I'd like to draw down a few points before the break. First one is, as I showed you, Darcy's law is a government flow in cross media under both saturated and unsaturated condition. The specific discharge, what is Darcy's law? It's proportional to the gradient of the total head. So total head constant is very important. But here we only need to deal with one constant, which is hydraulic conductivity. Under the unsaturated condition, then we have to deal with the two things. One is the permeability no longer a constant. It's a moisture constant. It's a characteristic function. The second one is the head itself, total head itself, depends on moisture content. And sometimes we call hydraulic soil retention curve. So these are the two characteristic curves. With that, we apply to Darcy's law. For steady case, we can actually answer the question: how the moisture distribute, how the pressure of nature structure distribute in the space if you know about time. So that's basically the break before the final section. Maybe we should take a 5 minutes break because I think it's all settled. So that's the study.